Hello, everyone. Great to see you all. Welcome. Welcome to FAU Harbor Branch Oceanographic Institute and the John and Barbara Ferreira Ocean Science Lecture Series. I've met so many of you before, but as a reminder, my name is Dr. Gabby McHenry, and I'm the Director of Education and Outreach here, as well as your host today. Today is the final lecture of a fantastic season. As many of you know, yes, we can give that a round of applause. We've gotten more rounds of applause this season than ever. I love you guys. As many of you know, we hosted presentations weekly since January, highlighting many different marine science topics happening here and around the world. We've had an amazing turnout, so between 125 and 240 people in person, as well as 40 to 70 people tuning in on the live stream each week. So it's been excellent. So I just wanted to thank you all for your participation and making this part of your spring schedule. It means a lot to us. Please also join me in thanking all of the amazing staff who support the series. It takes a team of more than 10 staff every week to pull off this program. And then, of course, as you know, we had 12 different speakers who took their time and shared their research with us. So we're very thankful for their contributions. The program wouldn't be what it is without them. And I hope, yes, you guys are the best. So I hope you all enjoyed the presentations and learned something new this season. I definitely did. As a reminder, all of our presentations are available virtually and they're recorded. So if you missed one or would like to watch one again, maybe even share it with your friends, you can pick your favorite one. You can find it on our website. And we have over 100 lecture recordings from decades of lectures there. So definitely check them out. We pretty much have something on every topic you might be interested in, especially if you're a newcomer to our series. So there's never a shortage of lectures. And of course, this isn't goodbye. Our Ocean Discovery Visitor Center is open year-round, and we offer many different tours and other educational programs for ocean lovers of all ages. And this even includes a program you may not be aware of called our Speakers Bureau, where we can arrange off-site presentations from our scientists. So if you're part of a club or a group who might be interested in that, I can help set that up for you. So just let us know. And we'll be in touch over email about the schedule for future lectures, as well as any special events. And we'll also be requesting some feedback from you all. So what you enjoyed this season and what you'd like to see in future seasons. So keep an eye out from that. And of course, you can connect with our team anytime. As always, I'd like to take a moment to thank those who support our programs, especially those who have made a donation to the Ocean Science Lecture Series, which so many of you have this season. Your generosity makes these lectures possible, helping us share groundbreaking discoveries and bring ocean science to our community. For those of you who joined us for our very first lecture back in January by our Executive Director, Dr. Jim Sullivan, you may remember that over half of the funding at FAU Harbor Branch comes from competitive grants. But as grant funding becomes more limited, philanthropy is playing an important role in advancing our mission. Donor support helps bridge this gap, providing critical resources for research, student training, and education programs that might not be possible otherwise. So if a topic from this season's lecture sparked your interest, whether it's protecting marine mammals to restoring critical habitats or exploring deep sea for new medicine, you can be a part of making that work happen, and your gift directly supports the scientists, students, and programs driving this discovery and conservation. So if you're interested in making a lasting difference through philanthropy, Brandon, and I would be happy to talk to you. And again, for one final applause, thank you for being part of our important mission here. So today, our season finale is titled Blue Energy in a Blue Economy by Mr. Gabriel Alsenas. who serves as the director at Florida Atlantic University's Southeast National Marine Renewable Energy Center. Prior to joining the center in 2007, Mr. Alsenas worked as a graduate student engineer for FAU's Department of Ocean Engineering, focusing on U.S. Navy future projects, prototypes, and sensor systems. He has led several major projects in marine energy, including build and offshore testing of current energy turbine prototypes, resource characterization, and novel test infrastructure and development. He has accumulated nearly 20 years of marine energy technology experience and over 10 years leading State of Florida Center of Excellence and U.S. Department of Energy University Center. He has a track record of public and private fundraising exceeding $25 million, industry and sector development, community engagement, and policy development. Mr. Alsenas was a key member of the team that secured the first offshore lease for renewable energy technology from the U.S. Department of the Interior. He holds leadership positions in U.S. industry trade associations for marine renewables and several officer positions in international standards. He was a founding board member and chair of the Conformity Assessment Committee with the American Renewable Energy Standards and Certification Association, former vice co-chair of the National Hydropower Association's Marine Energy Committee, and technical board founding member for the department's energy testing expertise for marine renewable energy networks. And he was selected as a recipient of IEC's 1906 award that recognizes exceptional individual achievements which helped advance EIC activities in a significant way. So as a reminder, for everyone here in person, we'll be hosting a meet and greet reception after the presentation with our speaker and some cookies in the gallery. So please make sure you join us for that. And let's welcome Gabe.
Good afternoon, good evening. Thank you very much, Gabby, and thank you very much to your team. I know how much hard work it is to put this series together, and it's, as she said and as we've seen, been quite a success so far. So another round of applause for Gabby and her team for this lecture series. And I'm not sure if you noticed, but I'd like to thank one of her team members, Chelsea, for conferring upon me a medical doctorate in the introduction slides, so I'll have to add that to my resume as well now. I first became involved with marine energy during my graduate studies, as Gabby said. This was in the mid-2000s, and my then dissertation advisor in the Department of Ocean Engineering here at FAU was the one who secured the original grant funding and the designation for our Center of Excellence at the state level. At the time, even though I was working on Navy projects, I started to help out with various things on the marine energy projects, and now, almost 20 years later, they can't get rid of me at all. For those of you who have attended this wonderful lecture series for some years, you may also remember that our chief engineer, Bill Baxley, has done a presentation in the past. His presentation was very much about the fun stuff, the technologies and the challenges that go along with trying to find ways to extract power from our natural resources offshore. But we also need to proactively work towards enabling a viable industry so that those companies that develop the equipment to capture the energy and turn it into useful things can also flourish as a sustainable industry as well. And so that's the vision that I plan to share with you today. Our State Center of Excellence, as I said, was established in the mid-2000s, about 2006. It wasn't until 2010 that the U.S. Department of Energy then recognized our activities and our potential contributions and designated us as a federal center. But over the past 20 years, we have led the world in a lot of the marine energy development technology activities with a special emphasis on what's in our backyard. And I'd like to talk a little bit more about that today. We've raised more than $25 million, closer to coming to $30 million now since 2006 for these projects. They have come from a variety of different sources, not just public funding, so a lot of industry funding and state funding as well. We have engaged more than 200 graduate students along the way, more than 25 faculty across 10 universities and national laboratories. So we see that as a great success, many of whom have also moved on to careers in the marine energy sector as it's sort of growing now. We've also partnered with more than 50 industry companies, and that to us is one of our pride points. We really believe that understanding and engaging with the industry partners is what makes us relevant and what gives us the opportunity to try to make this industry a success. So let's dive a little bit into how marine energy can help our communities, and one day we can benefit from these innovations. And I'd like to start sort of at the 30,000 foot level and make sure that everybody understands what these marine energy technologies are and how we participate in this world. So we're all familiar with a lot of these common renewable energy options, solar, wind, and biofuel. But what do they all have in common? They all come from the sun, one way or another. Obviously, the photovoltaics are a simple way to understand that that's actually converting the sun's direct rays into useful energy or power. But the wind is also driven by the differential heating and cooling of the Earth's surface, by the sun. So in an indirect way, wind is also a form of energy we extract from the sun. Same with the plants. The plants that we can use for fuels obviously need sun in order to be able to grow and flourish. But those aren't the only ones. That's not the only place in the world where the sun hides its energy. We know that it's also found offshore. It's found in gradients in the water, so that means that differing concentrations of either salt water or temperature in the water can be extracted and utilized by us to be able to get some useful energy and power out of it. But the vast majority of projects that we've seen over the last 20 years try to leverage the motion of the water, which is caused by the wind and other factors like those gradients in our oceans. The first one I'd like to discuss is waves, and sort of a natural way of thinking about it is that they can carry a lot of energy, and we know that, and especially surfers know that. We're used to seeing the waves that are on the right-hand side there, but those are the ones that we see here. They're not as powerful. They're not as useful to energy developers, especially if they want to develop projects that are at the utility scales. What they're instead looking for are waves more like what's on the right. And that's not something we see very often in Florida, maybe during storms, but that's not something that can be relied on for a continuous source of power. Once these technologies mature and then can scale, yes, there's areas of Florida that can benefit from this, but it's not on our sort of low-hanging fruit list of energies that we can extract from the oceans. Here's some examples of the kinds of technologies worldwide that are being proposed to be able to extract this energy. And you can see a lot of variety in the kinds of approaches. You know, we have bobbing things on the surface that take advantage of the up and down motions. We have sort of clam-shaped systems that flap up and down as the waves pass by in shallower waters. We have systems that are attached to the shore. We have systems that are installed independently offshore in different locations. And you'll also notice from the sampling that we have a variety of maturities of these technologies. Anything from conceptual pictures to systems that have been built and actually tested in the marine environments. Tides also offer opportunities to spin underwater turbines when the water is flushed in and out of constrictions. So as the moon pulls water on the earth back and forth, when the water flushes in and out of areas that have some sort of constriction, it creates high-speed flows. And those high-speed flows are what we can take advantage of with rotating machinery generally in those places in order to be able to create power. This is a very attractive opportunity for us for several reasons. One, it's predictable. We know exactly when that water will flow and at what magnitude and speed and direction. It's also usually found very close to land. So that means that transport cables and other things are cheaper and easier to install, maintain, and put in place. They're also very often found in shallower places, so not deep ocean depths. And for the same reasons, that's another advantage for these systems. But as many of us know, the Florida coast is a little bit too close to the equator, and our tidal changes aren't that dramatic. There are a few places in the Keys and other inlet locations that might be able to ultimately take advantage of these technologies when they get economies of scale. But it's also not one of the things that we here locally are looking at as sort of a primary way to get power to our communities sooner. Here's some examples of these technologies that we've seen around the world as well. A few things to notice. One is that many of them resemble conventional wind turbine configurations. So some sort of foundation or structure that supports a rotating turbine, rotor. They vary in terms of how many blades they have, how fast they spin, how close to the seafloor they are, how many are attached together, things like that. Whether they're attached to the sea surface, like we see in the top right. That's a full-scale commercial project that's in the UK at the moment. But we also see that there are some unique variations on it that don't resemble that archetype. And those have their own advantages. The one in the middle happens to be very useful in shallower waters. So if you find it in extremely shallow waters, that has an advantage than some of the other approaches that we see. What you'll also notice is that there's more photographs on this slide than there are renderings. And the reason for that is that it's easier to translate a lot of our existing technologies that we're already familiar with and have had market viability in wind turbines over to the water. Of course, it's not a simple challenge, but it is something that is easier to find components for and easier to install in the short term. And so we've seen a lot more development in this realm than the wave energy systems. We also have ocean currents. If you look very closely at this photograph, you'll see a Navy buoy, and in the far, far corner, you'll see a container ship that is passing by. What's interesting about this is that we don't see a lot of waves. We don't see very difficult offshore conditions. We see very calm conditions. We don't see the shore from here. What we do see is a very large wake from a buoy that was deployed in 2003, actually by our chief engineer when he was working for the U.S. Navy in Fort Lauderdale. The ocean currents are these massive rivers that flow in the oceans without shorelines. As they pass by objects that are moored in the current, they create these giant wakes, and that's what's interesting to see here. He actually said that this was something that you could see from an airplane as you came in and out of Fort Lauderdale Airport, because it was such a large wake that followed behind. You couldn't see the buoy, but you could see that large wake trailing behind it. It also has some very unique characteristics that we would like to explore more and take advantage of. So we focus on the power that could be generated from the world's open ocean currents, like our Gulf Stream that's offshore here in Florida. These are, as I said, massive rivers, but they continuously flow past our coast. About 30 million cubic meters of water per second flow by in this giant river. 30 million cubic meters of water. So if you make a cube that's a meter by a meter by a meter, 30 million of those cubes are flowing by our shores every second as it goes by. The speeds of the flow here average about 3 knots or 1.5 meters per second. And it's approximately 40 nautical miles wide, and it can be found about 5 miles offshore sometimes, depending on where its meander is. The core of the current, which is the section of the current in the middle that has the highest flows and the deepest area with flow, is usually found about 20 miles offshore. So this is a very large area that's relatively persistent in one place in order to be able to install equipment that would then take advantage of this flow. It's not the world's largest or fastest of these currents, but because of the Bahamian Shelf that constrains its flow to the Florida coastline, it is one of the most consistent and closest to shore of all the other currents found in shallower water than other currents around the world. So if you pair that with significant nearby port capabilities, large metropolitan areas, we have a great recipe for development. And that's why we think this is the place where these projects and technologies should be born. In 2013, Georgia Tech did a study that was reviewed by the National Academies of Science that took a look at how much of the Gulf Stream system could actually be extracted for useful power by our communities. Their result was this 163 terawatt hours per year, but unless you're in the utility industry, that probably doesn't mean much to you. What it does mean, using 2015 EPRI numbers, is that that could be about a third of the southeast U.S. states' demand in 1 year. It also could potentially power up to 15 million U.S. homes. So now it starts to become a very significant opportunity for us that isn't just something that Florida can take advantage of. But in Florida also, the study looked at it and said, well, just in the section that flows by Florida, how much can we capture? That's about 4 to 6 gigawatts. Again, if you're not in the utility industry, that probably doesn't mean much. But a good way to think about this is that the Turkey Point nuclear power plant in Miami and the Port St. Lucie nuclear power plant that's up here in this area are between 1.5 and 2 gigawatts capacity each. So you could potentially have 2 to 3 nuclear power plants worth of power in Florida alone from the currents. Portions of the water column have had slows or reversals based on hurricanes passing by or something like that. But those 30 million cubic meters of water are still trying to get by. So whether they get by at the surface or they get by on the sides or lower down by the seafloor, they're still getting by. So 24/7, there is always a flow of the current passing by our shores. This means that we now have what's called high capacity factors, and utilities that are looking for base load power means that you can rely on it when your consumers flip the switch in their homes or their businesses. That light bulb's going to turn on because that power is always there. Many other renewables are intermittent, and they require some sort of storage solution in order to be able to make sure that they are constantly available when the actual demand from your utility customers is there. The Gulf Stream and other currents around the world are unique in this way. So, how do we turn this into a reality, this wonderful opportunity? We can't just focus on the technologies themselves, the really cool gadgets and equipment that these companies are producing. Instead, we need to think of this as a system of systems approach, a challenge where these various aspects of a successful future commercial project are interdependent, and we need to make sure that we help support all of these interdependent areas. And as trained as an ocean engineer, it's not natural for us, but we have to recognize that even the technical solutions are sometimes and very often driven by socioeconomic factors or other factors. So we must consider them, and we must work to make sure that all of these balance in order for us to make this a potential commercial reality. And this is the strategy that our center has adopted. So a quick note about centers. We're one of four Department of Energy centers that are National Marine Energy Centers around the country. As you can see, we're spread across the different kind of corners of the U.S. Each of us has a particular focus on the types of marine energy that we find in our backyard. But we all collectively are working towards helping to provide the resources that our university has towards these goals. So if you think of a university's point of view, we're also looking at providing infrastructure to be able to test. So a variety of different companies can come and use the same infrastructure and leverage one investment in that infrastructure. We obviously train students as well. Many of the entrants into new markets are oftentimes the professional and white-collar jobs, and those graduates are from universities, and so we need to start targeting those as we spin up these workforce groups and start to be able to then better understand what kind of technicians and other things are needed, which, by the way, we're also working on starting as well. But we have another particular advantage, which is we're located in the places where these commercial projects are being proposed. So we have the opportunity to actually work with the stakeholders, the actual individuals, the communities, the regulators, the policymakers, the government officials, who are all involved in making decisions that affect the speed with which these projects can come to market. So this is a view of how we see that strategic vision of these interdependent systems coming together with our help. We view our primary mission as helping to stand up this viable marine energy sector. And I'd like to emphasize it's the sector. So you have to think about it as the whole supply chain. You have to think about it as the stakeholders, the communities, everything that's involved in making this an actual commercial reality. And we leverage the public, private, and dollars and the technologies that the industry has to be able to try to coordinate them and make them into a commercial reality. So we've worked hard to contribute to these different facets, and I'd like to go through quickly about some of these areas that we focus on. The first is resource characterization. We must understand the characteristics of these resources to pass on to the various technology developers and others, including the regulators, to understand how these technologies need to mature. So we've installed since 2009, almost on an annual basis, variety of current measurement capabilities. What you see on the left is buoys that we've installed for about a year at a time. They sit independently on the seafloor and they measure up in the water column to give us the direction and speed of the water as it passes by. These systems have limited battery and data life, so we have to collect them every once in a while, put them back in, refurbish them, put them back in. But we've also tried to take a look at the bigger picture by installing these coastal radar stations that you see there on the center and the right. These coastal radar stations use conventional radar waves to basically bounce them off the sea surface, bounce them back to shore, and we can interpret the direction and speed of the surface of the current as it's passing by. So our coastal radar stations currently cover about 30 miles offshore of Broward County and almost all of Broward County. And by adding one more station in Palm Beach County, we can then cover all of Palm Beach County and then onwards and upwards along the coast as needed. We also have technologies that we've developed to measure the turbulence in the water. So you can imagine that as this flow is going by, it's not just a perfectly straight flow. There's a lot of eddies and other turbulence that exists. This is important at various scales to the technology developers because it can help determine how long their equipment can last. If it's subjected to a variety of significant vibrations, its lifespan is reduced. So if we can characterize that vibration and help the companies know about it in advance, they can create ways to be able to mitigate some of that and increase the lifespan before they have to perform maintenance on those systems. We also help companies to develop their individual technologies. Whether that means building prototypes for them, it's a capability that we have here at FAU and especially here at Harbor Branch. We're very good at it. We've done it historically for many, many years. Or preparing in-house platforms that allow us to help benchmark the commercial system. So we've built small-scale turbines in-house as well with the intent that we can fully characterize them. There's no competitive concerns. There's no competitive advantage. But it's a known platform that we can publish about and we can help companies to then benchmark their technologies against without sharing some of their IP or competitive advantage. This also helps with components. So oftentimes you'll have a company that's focused on increasing the efficiency or performance of a particular component. Fielding an entire turbine and building an entire turbine is not necessarily cost effective to work on a particular component. So as we prepare these platforms, it also gives them the opportunity to leverage that rather than have to have the cost and expense of building an entire system to test a component. So we work to try to achieve this project success for companies, to advance the individual technologies, but also to build what we call market ecosystems. And I'd like to give you an example of that. So in 2017, we received a joint grant with a company out of Aventura, Florida called Ocean Current Energy from the Florida Energy Office, from the Renewable Energy and Efficiency Technologies program that they had. This funding was federal funding that flowed through the state to administer it. And under this program, we helped this technology developer build a prototype and demonstrate some unique features of their technology. And that's the one that you see on the top there. During May of 2020, we then had private investors, and despite COVID restrictions at the time, we were able to achieve a world's first. We demonstrated continuous power production offshore for 24 plus hours from that particular turbine that was built on a different program. So we had now state funding to build a prototype. We had federal funding that helped us support all the test infrastructure that we were able to put onto these ships that we used to be able to do this testing. And then we had private investors that helped us to bring it all together and be able to have that world's first and demonstrate this unique feature of ocean currents. We also provide platforms, but also do technology testing. And as manufacturers pursue their concepts, obviously it makes sense for an entity like a university or a national laboratory to provide these platforms so that multiple entities can use a single investment's worth of value. Onshore, we have several capabilities that are spread across FAU's campuses. We have a hydrodynamics laboratory that's down in Dania Beach at our CTEC research facility. That's an ocean and mechanical engineering faculty group. There's several tanks that allow us to characterize various things at scale. We also have the capacity with our faculty to be able to do numerical analysis and simulations, and this allows companies to be able to understand what characteristics their technology might have or conditions it might face without the expense of actually doing real-world build and testing. We've also built a laboratory dynamometer that we call the Ocean Current Power Generation Simulator. That's the little picture of the yellow system in the middle there. This system allows companies to come with just their drivetrain and be able to put it on this platform, and we've taken our measurements that we've had offshore and we've coded this platform in a way that it can actually simulate the way their rotor would turn their drive shafts and their generators under various conditions, but using the real-world data of the current that's found offshore here. So it's as close as they can get to simulate what power production they can have in a laboratory environment. We also have what's called a power in the loop simulation testbed. That's on our Boca campus at our engineering group that's there. We also recognize that these individual technologies have different ways of outputting that power. One may be at 480 volts and 60 hertz. One might be a different electrical configuration. All of these need to ultimately be integrated into the existing grid that we have if it's going to be producing power at scale. So the most economical way to investigate this, especially if you have very heterogeneous systems that are installed at the same time, meaning they produce different kinds of power and different kinds of power quality, is on a lab bench. And so we have sophisticated commercial technologies that come and they simulate utility scale grids. So the company can come and actually look at what it would be like to have 100 turbines or 1,000 turbines or 5 turbines, different configurations connected to an actual utility. We also have the ability to simulate other renewables in battery storage so that if it needs to integrate with these other community capabilities, how does that work? If there's a demand from a utility to take the power that's generated offshore and directly feed it to electric vehicle charging stations, how does that look? And how does that company tune its equipment in order to be able to have that value proposition? So these onshore capabilities allow us to do that, and DOE now has this Teamer program that provides support to us, not the developers, but for developers to be able to come and cover our costs in order to be able to do their testing. So these companies no longer have to go out and just find the independent funding just to do the tests that come here. They're able to find federal support for it. We also have inshore testing capabilities, and of course, some of you may recognize the channel, the private channel that we have here. We like to leverage this as well. This is sort of our rotor testing capability. We have a specially configured vessel that allows us to push rotors and other components ahead of the vessel into the free flow that's not affected by the boat's hull. And that allows us to then just take a look at the rotor components and understand how does it turn under different conditions? What is the power that it produces under different conditions? What if we stop suddenly? If, for example, a turbine needs to be braked in the field when it's out in the middle of the current doesn't stop. The turbines need to stop if we're going to have to take them in and out or perform other maintenance on them. So we can do all of that simulation and testing once it's gone through the laboratory test beds and start to do it under semi-controlled conditions that are here. We also have offshore testing capabilities, and that's how we did the 24-hour test. We leverage local charter boat assets. Sometimes we pull them from the Gulf of Mexico. Sometimes we pull them from the Cape Canaveral, depending on the capabilities that we need. But what we have here is we have the infrastructure that we then place on those ships that converts them into customized ships for turbine testing. And we're currently finishing up upgrading that infrastructure so that it can basically maximize the kinds of ships that we have available to us for towed testing of these systems. So this is the first time now that you expose the full turbine system in the actual environment to a flow, but we can control the flow because you can drive the boat faster or slower depending on what conditions you want to achieve. So we are now going to be able to test up to 60 kilowatt nameplate systems. That is approximately equivalent to about quarter to half scale systems that a lot of companies are proposing, and then about 5-meter overall diameter. We're limited by the kinds of ships that we have and the lifting capabilities that the ships have locally, but this will completely maximize our ability to help companies go through this particular testing evolution. On the horizon, we have just completed with an international engineering firm called EDAM out of Bilbao, Spain, under U.S. Department of Energy funding to do a final design of a test platform that can test up to almost 1 megawatt systems that can be taken all over the U.S. It can also test tidal systems and river systems in addition to ocean current systems. So this sort of one-stop shop platform can be taken and actually put in place for a longer period of time than you would have available if you were towing with a chartered vessel. Now you'd be able to place it in the environment where you have a potential commercial installation and be able to demonstrate it over a longer period of time to stakeholders and communities and utilities. So we are looking for follow-up funding in order to actually build this system. This was actually funding that came to us from before COVID, and our estimates for shipbuilding costs for this platform were about $4.5 million. After we completed the final design last year, the global supply chain issues had escalated those prices 4 or 5 times. So now the price tag for this is about $20 million to build this. So we are now coming back to a variety of other institutional investors and the federal government and looking to be able to plus up those dollars to be able to actually build it and field it, to be able to have it available to our customers. We also do ecosystem research. So here we've, as Gabby mentioned, we had the first lease to do marine renewable testing offshore. The lease was offshore of Broward County. The intent was to be able to have sort of test berth buoys that sat at the surface, and we could bring our towing charter boat capabilities, tie off to a buoy, and have a little bit more time than just if you were steaming along in the current for a few days to be able to do it. We went down the line to be able to go through construction operation planning and all the milestones that are required, and we decided that the sensitive benthic habitat that's offshore Fort Lauderdale on a feature called the Miami Terrace wasn't going to provide enough space for us to be able to do it there. So we're looking further north into the Palm Beach County and Martin County areas that have more sand and other remote areas that don't have as much coral activity and things like that, that we can make sure we're fine for those to put anchors on the bottom. But we also develop monitoring systems and do aerial surveys. We conducted 2 years of aerial surveys to look at all the major large animals, where they are throughout the year, what their activities are, see if we can coordinate and better understand what they do with respect to the current and the current's conditions, whether it's warmer, cooler, inshore, offshore. We've also developed some sensor systems that help us to better see what happens when animals are interacting with the equipment, to better be able to propose to resource managers and regulators exactly what we are experiencing, not just what we think we may experience in terms of risk to animals. All of these activities are meant to give regulators and resource managers the confidence that these projects are viable and safe, and there is a way that we can find a middle ground and a balance. And then out of all of our major activity areas, the final but not least is our education and outreach. As I mentioned before, we will need a future workforce, and we already have national and global workforce crises, so we need to get ahead of this as soon as possible in order to make sure that the workforce is properly familiar with and trained on this, So we developed a high school science class curriculum supplement. We trained over 200 teachers from the Florida Keys to the Treasure Coast. And we've also obviously done a lot of work with our graduate and undergraduate students that are at the university and other universities. We are hosting for the first time this summer what we call a short course that's going to be open to senior level undergraduates and graduate students. It's about a week boot camp that introduces them to the basic fundamentals and principles of marine energy development. And it will help them to better position in their degrees and the work that they do after their graduations to be able to contribute to the workforce. We hope that that and other activities that we do, and actually working with Gabby and her team, we're able to work all the way from K through 12 to graduate students and postgraduate students in order to really take a look at the full chain of the education outreach ecosystem. So now that we're kind of familiar with our center's activities, let's take a look at how it fits into the blue economy. And the blue economy is basically economies that are driven by any kind of maritime application. So we fit into that. We need to think bigger than these widgets that capture the electricity. So let's take a look at it from the project point of view. This is much like a traditional utility project. It's the same components, it's the same activities, but now it's offshore. Project developers assume the majority of the risk, but they integrate all of the parts and pieces of getting the turbine, the cabling, the electrical conditioning equipment undersea, the shore landings, and all of those other bits and pieces put together. They reduce their risk by working with insurers and regulators, certification bodies, warranties, to be able to then have contracts with the utilities at these large scales in order to be able to recover some of those dollars over a long period of time. Most of the time, these power purchase agreements are 20 plus years with many, many terms and expectations that then the utilities have the responsibility to distribute, transmit, and provide to the customer base. So understanding this from that point of view and helping our technology developers understand this from this point of view helps them to sort of have a less of an identity crisis. Many of our early technology developers tried to take on both at the same time because we really didn't have project developers stepping forward to say, hey, I will give you a purchase order for 1,000 of your turbines because I have this project that I'm building out there. So now we're finally starting to see these project developers get involved, and that to us is a sort of leading factor that helps show us that, yes, we've helped to get all of these technologies to a level now where we can start to engage and interact and help promote a lot of these other project level needs that they have. So our vision is to develop this blue energy innovation cluster in Southeast Florida. We want to anchor it with a full suite of concept to full-scale testing capabilities, so that draws all of the component manufacturers, the technology manufacturers, even the project developers to then see how these technologies work in the field. But we want to do it in a phased way. We want to strategically build it out for a variety of different reasons. One, because it helps us to navigate the regulatory pathways a little bit more efficiently. Rather than proposing a massive project from the start, we can go bite-size by bite-size from shore to offshore, where the regulations get more stringent. And we have more unknowns about what to do. So as we check off the knowns, the unknowns as knowns close to shore, we build out further offshore. But this also helps us to establish a supply chain. Rather than each company going out and buying its own anchors from a company, we can now engage with anchor companies that vie for a product line that specifically serves the marine energy community. So it helps bring them into this space as well, where otherwise they're not really attracted to it or involved in it. And then finally, and of course most importantly, is integrating with and engaging with the local communities and stakeholders. They're the beneficiaries of this in the long term. And so we want to be able to make sure that they have a say and they have a way of participating in this process in these early stages. An example of this is a U.S. Economic Development Administration tech hub that was recently designated and funded for almost $100 million out of Miami-Dade County, called the Risk and Resilience Tech Hub. The EDA saw that there were underserved and underfunded regional pockets of capability around the country in a variety of different sectors, not just our sector, that if funded would allow us to have global leadership in this space, but also allow that next step, sort of go from we've got things started to now let's expand it and grow it to something that's standalone and viable. So they're funding these areas, and as you can see, the consortium members that have been brought together here, and obviously FAU is one of the key consortium members, all of a sudden bring together now the investment community, the other stakeholders that we usually don't get to access and get to engage with. So this is a very valuable piece for us. The other thing that it does is, in this vision that they have for a resilient coastal community, it gives us the opportunity to now share resources with some of the adjacent sectors. So there are two other technology areas that we're working with. One is called green-gray infrastructure, which is basically the concrete and other infrastructure that's right at the coastline. So it kind of spans the transition between our land and our water. That's exactly where these projects live, or at least the interconnections to shore live. The other area is advanced materials, concretes, and methods for being able to develop concrete structures. That's very important to us as well, because many of the anchors that hold down these marine energy systems in the water are concrete anchors, but they have specific high technology needs that now we can help fill with partnerships from these other groups that are formally collaborating with us on it. Another example of this is a program that we are currently in the proposal stage for. The proposal's due April 15th, but we were invited after a second round in our partnership with the University of Miami and Florida International University to take those adjacent sectors that the Tech Hub has started to bring together for us, but now focus National Science Foundation funding on building an innovation engine that takes the innovations from the university specifically and help them to get injected into this whole ecosystem. So we're very excited about that. That would be $160 million over 10 years to help build this regional ecosystem. And then I'd like to touch on some of the local partnerships that we've built, because this is a very important aspect of it. Without this, we're just sort of working on this global scale without having a local touch. But since we are the regional representatives on behalf of the marine energy industry, it's important for us to do this. We have established some onshore and offshore infrastructure, but we need a partner, especially a utility partner, in order to be able to make this a reality. Florida Power and Light and other investor-owned vertically integrated utilities, as they're called, rely on that rate recovery, right? So in all of our power bills, we pay a specific rate that's been approved by the Public Service Commission in Florida, and that's how the funds are recovered by FP&L. There's not a lot of extra room for innovation funding or internal R&D. On the other hand, municipal utilities like the City of Lake Worth Beach not only have the same kinds of infrastructure that is valuable for the testing and interconnection, but it also potentially offers an economic impact back end that they can rely on. So as these companies move into the area and they start to frequent the businesses, they start to buy homes, they build commercial properties or rent commercial properties, that economic tax back end is part of the financial model of municipal utilities. And so this allows us to now start to leverage those relationships to get those higher risk, smaller scale systems online. We have been working with them to do an economic study. We've worked with them to be able to do a preliminary feasibility of what a potential interconnection with their grid might look like. And now we are currently working on a large-scale feasibility study to build out a grid-connected test facility interconnecting with the City of Lake Worth Beach that's funded by the U.S. Department of Energy. We hope to have some preliminary results in the next year and a half that will help us move to the next stage, which is more detailed engineering for it. So we have all these wonderful opportunities. How can you help? And you've seen these slides before, but I would like to include this from sort of a personal touch from the point of view of our center. For us, building community support for it in a variety of different ways, even at the local individual level, has an incredible value. As our elected officials hear more and more from our communities that this is important to them, it becomes an important issue then that as we're working with them to be able to get funding and other resources, it allows us to be able to then better, to get those quicker and to be able to align them more with the community needs and make the conditions more favorable for marine energy development. From the giving side, I would like to, we've seen that our center has been successful getting these large sums of money, but a lot of things that we do from a technology point of view are very expensive. There are also a variety of other things that don't have $1 million plus price tags that are very valuable to us that we cannot pay for by rule or law from the grants that we receive. Oftentimes the grants that we receive are scope driven, so they're specifically to pay for the activities of that sponsor's needs. Things like education outreach, participating in programmatic meetings, building out industry advisory groups, things like that are not something that we have support from those mechanisms. So we've relied on a variety of industry preferred partner programs and other private donations to be able to support those activities. So to us in our center, even though we have big price tags for the technology, it really does enable us to operate the center and make it sustainable over a long period of time. And I think as some of you have already participated in, we have a survey. This is an important aspect of our community outreach now. We'd like to baseline exactly where the community is in terms of the marine energy projects and our center's activities. And this will help inform a strategy to be able to get out into the community and make it known about our projects and to touch especially on the points that the community is interested in and align our projects with those things. So please take the time to either use this QR code to fill out the survey. I know there's more clipboards and surveys out in the reception area as well. But this is an important aspect of our engagement with the community. So thank you very much, and I'd like to take questions. Yes. So the question was, what are my concerns for continued government funding from those resources? So, every 4 years, and we've been at this for 20 years now, every 4 years there's generally been a administration change. I think one of the wonderful things about the projects that we work on is that they have cross-aisle value and cross-aisle interest. I found that in my personal engagement with our legislators at the state and federal levels. We're fairly confident that we'll be able to continue to attract support for these projects, but it's very helpful to continue to have the public support filter up through our legislative representatives so that when they sit in the committees, when they sit in the appropriations committees and other committees, it allows us to have influence and pathways to be able to continue. Yes? So the question was, how many people on our team? It's a huge project. Yeah, I agree, it's a very huge project. Our strategy, we have at some points in time had 15 or so staff full-time that were on the project. We noticed that we weren't leveraging the university's resources as much as we possibly could. So what we started to do is work with teams like Gabby, who are the experts in the education outreach. We don't need to try to find additional or extra experts in that field. So we actually have less than half a dozen actually full-time paid employees or faculty members by the center, but we work with all of our university partners and within the university to be able to get the resources that we need in order to be able to do it. Yes, sir.
How far do you think you are away from commercial?
I used to say that's the $1 million question, but I don't think $1 million goes that far anymore these days. So the question was, how far away are we from commercial development? I used to try to have a crystal ball and give estimates, but I've been proven wrong so many times that I've stopped giving those estimates. The best I can say is that as we move along, there are touch points that we see that encourage us that major milestones are being hit by the industry. And as we see those major milestones, whether they're with individual companies, groups of types of companies, or with our project developers getting involved, our utility interest, we're able to start to see that horizon and be able to see it. You know, I couldn't tell you if it was 5 years, 10 years, where it might be. In engineering, you know, you can solve any problem if you throw enough money at it. It's just a matter of how quickly you can do it. And I think that we're in a similar situation. If we had all the money that we needed in order to be able to do it as a sector, it would be quick. But we have to kind of put together this portfolio that can keep us moving along strategically and still achieve those outcomes. Yes, real quick. Yes, sir. Yeah. Yeah. Yeah, so the question was, please explain further the plans with Lake Worth Beach and how we engage with them with these offshore test area capabilities. So I didn't think we had time today to get through some of the details of what our specific technical vision for that was, but we noticed that, as you mentioned, the real sort of full, what we call the fire hose of the Gulf Stream, is 20 miles offshore. That's where we eventually need to get to. But most of the technology scales that we see that are ready to get into the water aren't there yet either. So our goal is to try to pre-pace the technology needs as we move further offshore. Let me explain a little bit. So inshore, between about 3 miles and about 5 miles, we do see current occasionally. And there's an advantage to that. If you're out in the 20-mile core of the Gulf Stream, there's no way to turn the Gulf Stream off. So you have to have all kinds of novel ways to be able to put equipment in and out of the water without exposing them to those extreme forces that they would have to be if you're just sort of standing still and trying to put something into a 5-knot current. Inshore, we can place equipment, occasionally get it exposed to the current, but not full time. So there's some advantages, and we've had some companies at the smaller scales ask for that capability rather than having to graduate immediately to sort of full forces that are offshore. We also see a potential opportunity for the nearshore smaller scale systems to connect to areas that might need power that are offshore that might not want to pull a power cord from onshore to offshore. A couple of examples, we've had some proposals to put offshore data centers there. One of the advantages that if anyone has seen any of these data centers that we build on land, the greatest cost of those data centers is cooling it, keeping it cool. And that cooling cost is what is driving the power costs in most of these facilities. So if you take that server farm and you put it underwater where it's cold, you immediately gain some of the benefits of having it cool down, but then you may also gain additional benefits by having a co-located power generation system. So these generation systems can directly power that without having to go onshore and back offshore kind of thing. So there are some potential nearshore and midshore opportunities that we think we can leverage before we get to the full offshore interconnection points. And the other advantage, just really quickly, sorry, is that the city of Lake Worth Beach doesn't just want to get power from offshore, it also has power to give from onshore. So a lot of these early systems aren't self-sufficient from a power point of view either. So that power cable has to sort of be bidirectional in the first place. So you can't just put a dead cable in and hope to get power on the other end. You need to have both sides. I think I saw a question back there. I think, yes. Yeah, there's a lot of activity in the UK. There's very mature tidal projects that have been installed at full scale that produce power to the grid. In the US, we've had just a handful. We had a project that was in the water for almost a year in the East River in New York City, a company called Verdant Power that had 3 turbines that were placed in the East River by Roosevelt Island and produced power, a significant amount of power to demonstrate those capabilities. We also have a company that's headquartered in Portland, Maine, that has had equipment in Maine, in the water, producing electricity and connected to the grid, but also the similar technology but scaled down in rivers in Alaska. You can imagine that some of the remote communities there don't have access to power in the first place, but also their power costs are higher. So entry into those markets is a little bit easier at the smaller scales for some of these companies. Yes, ma'am. Oh, yes, sir. So the question is, are there any studies on the impact on marine life? Yes, and we have done many of those studies. We want to be able to understand the risk to those particular animals, whether it's individuals or populations of those animals. So that's why we did the aerial surveys, to basically understand where they are during times of year and what they're doing and how that might interact with the equipment that's in their areas. But also then understanding when they actually go and interact with the equipment, is there a risk to those animals? So we do a variety of sensor development to understand it, so when projects go out in the water, we'll be able to capture that. A lot of the regulatory agencies take what's called an adaptive management approach, which basically says, let's manage the risk to a point that we are comfortable with, and then over-observe the interaction so that we can then get the data that we need in order to understand how the populations and stuff work. And so we participate with them in those programs as well. Did you have a question? So the question is about biofouling and how that factors into the economics and the technologies that are being built. So absolutely, that is something that's recognized. There's still a little bit of work to be done to understand fouling at the speeds that these systems are exposed to the water. So for example, anti-fouling for a vessel is 8+ knots of speed, of relative speed between the vessel and the flow that it's exposed to. All of our technologies that are commonly available on the marketplace are designed for preventing fouling at those speeds. These systems are in slower water. So does that mean that it accumulates more? How does it accumulate? Are there coatings that can be appropriately designed in order to be able to prevent the fouling? And then the operations and maintenance of these systems has turned out, from our UK partners that have had full-scale systems for longer periods of time, it turned out to be the cost drivers in many cases. So making sure that this equipment can actually last the 20-year power purchase agreement lifespans is one of the major challenges that these companies face for it. Do I have time for one more?
One more.
One more. Yes, ma'am. So the question was, what is our concern in terms of climate change collapsing the Gulf Stream system? So there have been a couple of studies that we've seen in the past few years that have been in the public domain on both sides of that front. What I can tell you is that our measurements sort of don't lie, and we've had measurements that match the last 30, 40 years of measurements that have been done in other ways. And so far we haven't seen a major change, dramatic change in the amount of energy flux, flow, or any of those features. And when I was a young graduate student, first attending conferences and answering questions about these projects, I remember that was one of the first questions I was asked. And I remember thinking about it later and realizing that if we have a collapse like that, then putting marine energy in our waters is nowhere near our highest concern at all anyway. So we'll just keep plugging away and try to make this a commercial reality to help. Yes, ma'am. So we have a participant from northern Spain where we had a partner that built that designed the floating test platform, and the question was, have we had help from Iberdrola, which is in that area? Not directly. A lot of the project features are specific to the U.S. waters and the kinds of technologies that we expect to see in the pipeline. Although we did work quite a bit with a lot of the European developers, we've seen a strong interest from some of those mature tidal developers in the UK to take their technologies and bring them here in our backyard. So that might help accelerate our access to the commercialization as well, if we can get those imported. Yep.
All right, everyone, join me in thanking Gabe for his great presentation. Excellent, excellent work. Well, that is a wrap on our 2025 Ocean Science Lecture Series. Thank you all so much for joining us. Please join us in the gallery to take that survey to help direct our education and outreach. Grab some cookies, chat with Gabe and I, and we look forward to seeing you next year. Thank you for so much for coming.